In this video, we're going to review Newton's theory on the celestials and Albert Einstein. And it's going to lead us towards this new theory that's being developed based on the idea of Newton's equation for mass, for actually E equals mm squared relative to the mass between the planets. Well, in this video, I'm going to tell you what's in between the mass of these planets. Something Einstein neglected, and it'll give you a pretty good explanation of what's going on. I hope you like the video. Thank you.
Up at the night sky, dotted with countless stars. Each one of those tiny points of light represents a distant sun, many of which have their own planets orbiting them. The vastness of the night sky is a window into the enormity of the universe. Now imagine yourself shrinking down to an incredibly small size, smaller than an atom. At this scale, you would enter a world of subatomic particles where the rules of physics as we know them start to change. It's a realm where quantum mechanics reigns supreme. From this perspective, you would see that those stars are not just points of light, but massive balls of burning gas, gathered together in vast swirling galaxies. Each galaxy contains billions of stars, and each star could potentially host its own solar system. Our sun, the star that gives us life, is just one of billions of stars in the Milky Way galaxy. It sits in a relatively quiet neighborhood of the galaxy, providing the perfect conditions for life to thrive on our planet. And the Milky Way is just one of billions of galaxies in the observable universe. Each galaxy is a vast collection of stars, planets, and other celestial objects, all bound together by gravity. It's a truly humbling thought, isn't it? To think that our planet is just a tiny speck in an immense cosmic ocean. The more we learn about the universe, the more we realize how small we are in the grand scheme of things. To understand the universe's expansion, we must first grasp the sheer scale of it all. The distances between stars, galaxies, and galaxy clusters are so vast that they are almost beyond human comprehension. Our cosmic address is a journey through ever larger structures, from our solar system to the Milky Way, to galaxy clusters and beyond. Each step takes us further into the depths of the universe, revealing more about its structure and composition, and finally, to the vast cosmic web that stretches across the observable universe. This web is a complex network of galaxies and galaxy clusters, interconnected by vast cosmic filaments. But what lies beyond the observable universe? The edge of what we can see is not the edge of all that exists. There could be countless more galaxies and cosmic structures beyond our current reach. What secrets does the cosmos hold beyond the reach of our most powerful telescopes? As our technology advances, we continue to push the boundaries of our knowledge, peering deeper into the universe than ever before. These are the questions that have captivated astronomers and cosmologists for centuries. The quest to understand our place in the universe is a journey that continues to inspire and challenge us, driving us to explore the unknown. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery. His observations would forever change our understanding of the cosmos and our place within it. He observed that galaxies are moving away from us, a revelation that was both astonishing and perplexing at the time. And the farther away a galaxy is, the faster it's receding. This relationship between distance and speed was a pivotal clue. This observation, now known as Hubble's law, provided the first concrete evidence that the universe is expanding. It was a monumental step in cosmology. But how do we actually see the universe expanding? It's not as if we can watch galaxies drift apart in real time. We can't observe space itself stretching, so we rely on indirect methods. These methods involve careful measurements and sophisticated technology. One such method is measuring the redshift of light from distant galaxies. Redshift is a key indicator of how fast an object is moving away from us. Imagine the sound of a siren moving away from you. As it moves, the sound waves stretch out. The sound waves stretch out, causing the pitch to decrease. This is known as the Doppler effect. Similarly, as light travels through expanding space, its wavelength stretches, causing it to shift towards the red end of the electromagnetic spectrum. This stretching of light waves is what we call redshift. This is known as redshift. It's a fundamental concept in understanding the dynamics of our universe. By measuring the redshift of light from distant galaxies, astronomers can determine how fast they are moving away from us. This data is crucial for mapping the expansion of the universe. Providing further evidence for the expansion of the universe, redshift measurements have become a cornerstone in cosmological studies, helping us to piece together the history and future of the cosmos. It's important to understand that the expansion of the universe is not like galaxies flying away from each other through space. Instead, it's the fabric of space itself that is stretching, carrying the galaxies along with it. Think of a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, representing galaxies, move farther apart from each other. But the raisins themselves are not moving through the dough. Rather, the dough itself is expanding, carrying the raisins along with it. Similarly, the expansion of the universe is not due to galaxies moving through space, but rather the stretching of space itself. This stretching is happening everywhere, all the time, on a cosmic scale. Another helpful analogy for understanding the universe's expansion is to imagine a balloon with dots drawn on its surface. Each dot represents a galaxy. Now, as you inflate the balloon, the dots move farther apart from each other. The surface of the balloon represents the three-dimensional space of our universe, and the inflating balloon represents the expansion of space. As the balloon expands, the distance between any two dots increases, just as the distance between galaxies increases in the expanding universe. It's important to note that this analogy has its limitations. For example, the balloon analogy might lead you to believe that there's an outside to the universe, which is not necessarily true. However, it provides a useful visualization for understanding how the expansion of space causes objects to move farther apart. Section 5. The Great Debate: Is our universe infinite or finite? One of the most fundamental questions in cosmology is whether the universe is infinite or finite. While the observable universe has a defined boundary, the farthest we can currently see, the universe itself might extend infinitely beyond that horizon. Imagine yourself standing on the surface of a very large sphere. You can walk in any direction, and you'll never reach an edge. This is what it would be like to live in a finite but unbounded universe. A universe that is finite in size but has no edges or boundaries. On the other hand, an infinite universe would extend forever in all directions. It's a mind-boggling concept, but it's one of the possibilities that scientists are currently considering. Section 6. The shape of the universe, a cosmic enigma. The shape of the universe is another perplexing question that astronomers are grappling with. Based on current observations, the universe appears to be remarkably flat, meaning that parallel lines will remain parallel forever. Think of a flat sheet of paper. You can draw two parallel lines on it, and they'll never intersect. This is what it means for the universe to be flat. However, other possibilities exist. The universe could be positively curved, like the surface of a sphere, or negatively curved, like the surface of a saddle. Each of these shapes would have profound implications for the fate of the universe. Section 7. The ever-expanding horizon, unveiling the secrets of the cosmos. As the universe expands, the observable universe also grows. This means that over time we can see farther and farther into the past. It's like watching a movie in reverse, with each new frame revealing a more ancient epic of cosmic history. The most distant light we can currently detect is the cosmic microwave background radiation, a faint afterglow of the Big Bang, which occurred approximately 13.8 billion years ago. This radiation provides a snapshot of the universe in its infancy, just a few 100,000 years after the Big Bang. By studying the cosmic microwave background and other distant objects, astronomers are piecing together the history of the universe and unraveling its mysteries. Section 8. The ultimate fate of the universe, a cosmic mystery. The fate of the universe is intimately linked to its expansion. This expansion has been ongoing since the Big Bang, and it shapes the very fabric of our cosmos. If the expansion continues to accelerate, as current observations suggest, the universe will eventually end in a big freeze, with all matter and energy becoming increasingly dispersed and diluted. In this scenario, galaxies will drift apart, stars will burn out, and the universe will become a cold, dark, and desolate place. Imagine a cup of coffee cooling down. The process is gradual but inevitable. As it loses heat, the coffee molecules slow down, and the coffee eventually reaches room temperature. This is a simple analogy to understand the Big Freeze. Similarly, in a Big Freeze scenario, the universe will continue to cool down and expand, with stars eventually dying out and galaxies drifting farther and farther apart. Over billions of years, the cosmos will become a vast, empty expanse. However, other possibilities exist. The ultimate fate of the universe is still a subject of intense scientific debate and research. The expansion of the universe could eventually slow down, leading to a big crunch where everything collapses back in on itself. In this scenario, the universe would end in a fiery, dense state, possibly giving rise to a new Big Bang. Alternatively, the universe could reach a state of equilibrium, where the expansion continues at a constant rate. This would result in a steady-state universe, where galaxies remain at constant distances from each other, balancing the forces of expansion and gravity. As we continue to observe and study the cosmos, we may uncover more clues about the ultimate fate of the universe. The mystery remains, but each discovery brings us one step closer to understanding the grand design of our existence. Section 9. Beyond the horizon, the unknowable vastness. The vastness of the universe is both awe-inspiring and humbling. The observable universe alone contains billions of galaxies, each with billions of stars, and we are just beginning to scratch the surface of understanding its complexities. The concept of an expanding universe has revolutionized our understanding of the cosmos, but it has also raised more questions than answers. Is the universe infinite or finite? What is its shape? What is the ultimate fate of the universe? These are questions that will likely continue to captivate astronomers and cosmologists for generations to come. As we continue to explore the cosmos, we can be sure that the universe will continue to surprise and amaze us with its wonders. The vacuum field is negatively charged due to the positive planetary matter of celestial sort. A ship travels under the influence of the dark grid, meaning it mimics its zero-point polarity, zero mass. It's the Hubble anomaly that the age of the universe flows to. Positively excited planetary matter, the stars, planets, and galaxies, excite a negative resistance under Newton's law. The foundation is that positive similar matter stays separated in the same manner as two positive magnetic poles repel each other. This evident space between similar entities generates negative grounding. As the universe ages over time, its positive decay energy is absorbed through the negative space field and flows to the Hubble anomaly, generating universe expanse. In turn, weightlessness and a zero-point vacuum warp drive nature's system in the universe. Zero-point energy space retains no energy to cause inertia or time dilation that advocates relativity's laws if universal constant. No theory of this observation exists. Classical physics and Einstein's gravity still dominate physics, yet net values are set in motion by the quantum physics theory that illustrate opposition. Relativity asserts its gravity laws on space curvature, which is true to the effect of planetary bodies generating acceleration, but also claims the speed limit in zero vacuum. You can't have the cake and eat it too, so he enters no real arithmetic to his inquiry. Space is the same to all observers. If it weren't, space would be different in many areas. Space meaning dark matter. The heavenly bodies are all limited to the speed of light, constant under the influence of their own energies. Infinite mass is reincorporated in quantum physics into a weightlessness space matter condition that applies to all matter, even the planets and the stars. But yet, they are not in relativity. Relativity rejects this assumption, this fact about space, so who is right, and if the vacuum assumes energy over time used up by motion activities of a kind, causing celestial humanoid organic matter to age and celestial bodies to burn energy over time, where does that energy flow to? Dynamic landscape that can be tapped into for travel or field manipulation. It redefines inertia and motion as functions of quantized space behavior. Predicts new forms of energy or motion that emerge from field alignment with expanding space. Offers theoretical propulsion systems that sidestep relativistic constraints. Quantum physics. Dark energy within the quantum physics framework, such as Rodney Kowecki's model, is a reinterpretation of the mysterious force driving the accelerated expansion of the universe. Unlike standard cosmology, which treats dark energy as a constant or scalar field, like the cosmological constant in general relativity, quantum physics offers a more structured, field-based interpretation. The quantum physics dark energy first, field-based vacuum dynamics. Dark energy is not just a passive, constant energy, it's an active, quantized field embedded in the geometry of space. It operates as a reverse vacuum pressure, pushing space-time apart by acting on quantized space units. Non-energetic propulsion potential. This vacuum field may interact with massless or low-mass particles without direct energy transfer, enabling propulsion or warp dynamics without fuel. It implies gravitational repulsion, similar to anti-gravity effects in certain field configurations. Spatial inversion and acceleration. Dark energy in quanta physics is tied to spatial inversion or stretch mechanics. Space stretches uniformly due to a built-in property of its quantized fabric. This helps explain not just expansion but acceleration as a geometric effect rather than purely energetic. Faster than light. In advanced interpretations, the dark energy field aligns along cosmic corridors, low-density channels through which faster-than-light vehicles could move with minimal resistance. Time and mass. Some quantum models propose dark energy also affects time dilation and inertial mass, modifying how objects behave across large distances or at high velocities. Comparison cosmology. Standard cosmology versus quantum physics theory is the nature of dark energy. In standard cosmology, we have the cosmological constant or scalar field. On the other hand, quantum physics theory suggests a quantized reverse vacuum field. When it comes to the energy source, in standard cosmology, it is intrinsic to space. Meanwhile, in quantum physics theory, it emerges from the space quantization structure. Its role in expansion can be seen as a passive driver of acceleration. However, it also plays an active role, driven by fields, in both expansion and propulsion. When it comes to interaction with matter, there's no direct interaction, but there's potential for geometric or field-based interaction. As for its application to propulsion, traditionally, there is none. Yet it can be used for faster-than-light drive corridors. In quantum physics theory, a ship can theoretically travel at superluminal or faster-than-light speeds without interrupting space-time. This is because the motion does not rely on traditional acceleration through space. Instead, the framework proposes an entirely different mechanism for achieving these incredible speeds. The key mechanism here is field manipulation over locomotion. The ship rides within a modified quantized vacuum corridor, often described as a reverse vacuum field or dark energy channel, which restructures the local properties of space itself. Space-time flow alignment is another fascinating concept. Instead of pushing through space-time, the ship aligns itself with the directional flow of expanding space, kind of like surfing a wave. This clever method avoids relativistic mass increase and time dilation. Non-disruptive interaction is crucial for maintaining space-time integrity. Since the drive field is integrated with the quantized units of space, there's no tearing or breaking of space-time continuity. Instead, the vacuum field forms a topological bypass rather than an energetic thrust. To put it simply, think of it like skipping stones across the surface of a river without touching the water. Each quantized step is a real point in space, but the path cleverly avoids normal space friction and temporal resistance.
In the late 17th century, a young Isaac Newton revolutionized our understanding of the universe. Legend has it that an apple falling from a tree sparked his groundbreaking realization. Newton deduced that the same force pulling the apple to the ground also governs the motion of planets and stars. This force, he realized, was gravity, a universal force affecting all objects with mass. Newton's insight challenged the prevailing notion that different laws governed the heavens and earth. He proposed that gravity was not limited to our planet, it extended far beyond, holding celestial bodies in their orbits. This revolutionary idea laid the foundation for his groundbreaking work on the laws of motion and universal gravitation. In the late 17th century, a young Isaac Newton revolutionized our understanding of the universe. Legend has it that an apple falling from a tree sparked his groundbreaking realization. Newton deduced that the same force pulling the apple to the ground also governs the motion of planets and stars. This force, he realized, was gravity, a universal force affecting all objects with mass. Newton's insight challenged the prevailing notion that different laws governed the heavens and earth. He proposed that gravity was not limited to our planet, it extended far beyond, holding celestial bodies in their orbits. This revolutionary idea laid the foundation for his groundbreaking work on the laws of motion and universal gravitation. Newton's law of universal gravitation, mathematically expressed as F equals g times the product of m1 and m2 divided by r squared, quantifies the gravitational force between any two objects. This elegant equation states that the force is directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between them. The gravitational constant ensures the equation's universality. The implications of Newton's law were profound. It provided a unified explanation for both celestial and terrestrial phenomena. The same force that caused an apple to fall could explain the moon's orbit around Earth and the planet's orbits around the sun. This unification of previously disparate realms marked a pivotal moment in the scientific revolution. While Newton's theory of gravity revolutionized our understanding of the universe, it wasn't the final word. In the early 20th century, Albert Einstein, with his theory of general relativity, offered a radically different perspective on gravity. Einstein proposed that gravity is not a force acting across space, but rather a consequence of the curvature of space-time itself. Imagine a trampoline. Placing a bowling ball in the center causes the fabric to sag, creating a curvature. Now, if you roll a marble across the trampoline, it will follow a curved path around the bowling ball drawn by the dip in the fabric. This analogy helps visualize how massive objects like stars and planets warp the fabric of space-time, influencing the motion of objects around them. General relativity made several startling predictions, later confirmed by observations. These include the bending of light around massive objects, a phenomenon known as gravitational lensing, and the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. Both Newton and Einstein's contributions to our understanding of gravity are monumental. Newton's work provided a unified framework for understanding motion and gravitation, laying the foundation for classical physics. His theories enabled countless scientific and technological advancements, from predicting celestial events to launching satellites into space. Einstein's general relativity revolutionized our understanding of gravity, revealing its intimate connection to the fabric of space-time. His theory predicted phenomena like black holes and gravitational waves, ripples in space-time caused by the acceleration of massive objects, further enriching our understanding of the cosmos. The legacies of Newton and Einstein continue to inspire generations of scientists. Their work serves as a testament to the power of human curiosity and the pursuit of knowledge. As we delve deeper into the mysteries of the universe, their profound contributions will forever shape our understanding of the cosmos and our place within it.
In space, mass diminishes because of the vacuum field. The vacuum field is negatively charged due to the positive planetary matter of celestial sort. A ship travels under the influence of the dark grud, meaning it mimics its zero-point polarity, zero mass. It's the Hubble anomaly that the age of the universe flows to. Positively excited planetary matter, the stars, planets, and galaxies excite a negative resistance under Newton's law. The foundation is that positive similar matter stays separated in the same manner as two positive magnetic poles repel each other. This evident space between same similarities generates negative grounding. As the universe ages over time, its positive decay energy is absorbed through the negative space field and flows to the Hubble anomaly, generating universe expanse. In turn, weightlessness and a zero-point vacuum warp drive nature system in the universe. Zero-point energy space retains no energy to cause inertia or time dilation that advocates relativity's laws if universal constant. No theory of this observation exists. Classical physics and Einstein's gravity still dominate physics, yet net values are set in motion by the quanta physics theory that illustrate opposition. Relativity asserts its gravity laws on space curvature, which is true to the effect of planetary bodies generating acceleration, but it also claims the speed limit in zero vacuum. You can't have the cake and eat it too. Space is the same to all observers. If it weren't, space would be different in many areas. The heavenly bodies are all limited to the speed of light, constant under the influence of their own energies. Infinite mass is reincorporated in quantum physics into a weightlessness space matter condition that applies to all matter, even the planets and the stars. But yet are not in relativity. Relativity rejects this assumption. So who is right? And if the vacuum assumes energy over time, used up by motion activities of a kind, causing celestial humanoid organic matter to age and celestial to burn energy over time, where does that energy flow to?
Hello, I'm back. Bringing together this new concept in Einstein's theory. So, as a finishing end, this is called new concepts in advanced physics. Anyways, Einstein describes his space as having a surface and a planet impressing its weight on it, creating a bending in space underneath the planet. Now, like a trampoline, you roll, let's say, a bowling ball on it, and it's going to make an impression. And that's the way he explains the what space is as a surface. Now, with new AI reinventing ideas, new physicists coming into play and creating and capitalizing or modernizing advanced physics, which relativity is 100 years old. It's behind its time. There's a new concept for a surface. If you go outside and look at the stars and everything, take your camera and take a snapshot. Take that snapshot and put it through a printer, lay it out on a table, and you have a map of the universe. This is a new concept in Einstein's theory by who, I don't know, but I come across it. Anyways, I hope you like my video. Quantum physics theory. It's a new theory, and it gives a solution as well as equations for faster than light space travel and what it is that dark matter, dark energy is, and what's happening with it. Thank you.